So if you recollect, we were looking at frequency response, which is the response of stable LTI systems to sinusoidal inputs, and we were interested in figuring out how the steady state response of this class of systems would be. I know because it's practically useful, right? Because we can give sinusoidal inputs in practice, measure the output, and try to figure out the system transfer function from that output measurements. Okay, so that is where there's a practical application, and we saw that for linear time invariant systems which are stable, the state input is also a sinusoid of the same frequency, but scaled in magnitude and shifted phase, right? And that depends on the sinusoidal transfer function P of j omega. So P of j omega becomes a very important quantity for us, right? So from that perspective, we need to figure out how we can represent P of j omega. So what we do is that, like, we started off with what is called as the Bode plot, because P of j omega is a complex quantity. It has a real part and imaginary part, or alternatively, it has a magnitude and a phase. So we started off with a discussion of the Bode plot, and we are going to spend the next few classes learning about the Bode plot, right? So we will figure out how to construct the Bode plot, and then learn how do we interpret things from the Bode plot, right? As we go forward. Okay. So this is a recap of where we were, and so let's get started with our class today. Okay, so we are going to learn about the Bode plot. So as we learned, so it has two plots. What is called as a magnitude plot, which plots the magnitude of the sinusoidal transfer function P of j omega, which is the frequency omega, and the phase plot, right, or the angle plot, where we plot the angle of P of j omega, which is omega. So if we look at the magnitude plot, people also call it as a log magnitude plot. The reason will become clear. What we do in the magnitude plot is that, like, we plot the magnitude of the sinusoidal transfer function P of j omega in a metric called decibel measure. So in the decibel measure, we take the logarithm to the base 10 of the magnitude of P of j omega and then multiply it by 20. Okay, so that's the definition of decibel metric. And we plot the frequency omega on the x-axis using a logarithmic scale. Okay, so now it is, I hope it's clear why we call it as a log magnitude plot, right? Because we are taking the logarithm of the magnitude of the sinusoidal transfer function. Now, what are the advantages of using a decibel measure, and also what are the advantages of using a logarithmic scale for the frequency? Let's figure it out. So all of us know about a linear scale, right? So if we take our linear scale, we have markings 0, 1, 2, 3, etc. Right? So if you use a linear scale for omega, the point is, if we take any two sets of consecutive equidistant points, the difference between those 2 points will be equal. Okay, so if we subtract 2 and 1 and we subtract 3 and 2, the difference is 1, right? It's equal. On a logarithmic scale, what happens is that we have equidistant points to have the same ratio. Okay, that's when they are equidistant in the logarithmic scale. So if we take logarithm to the base 10, if we take 0.01 and 0.1, the distance between them will be the same as between 0.1 and 1, and which will be the same as 1 and 10. Okay, so essentially the ratios will be the same. So this is a unique feature of a logarithmic scale. Okay, so easy way to remember difference between linear scale and a logarithmic scale is that in a linear scale, the difference between two sets of equidistant points will be the same. Whereas in a logarithmic scale, the ratio of values of two sets of equidistant points on that scale will be the same. Okay? So now, what are the advantages of such scales? The advantages immediately obvious from these two plots, right? Using a logarithmic scale, we can plot a larger range of frequencies. See, if you look at the first plot, we could plot only from omega equals 0 to 10. Whereas in the second plot, we could plot from 0.01 to 10 power 3. Okay, so that's a huge range of frequencies. Okay, so that's one advantage of a logarithmic scale. And another thing is that you and I can expand the low frequency region. Okay? That is an important advantage which you will realize as we go along, because many physical systems, right, the critical frequency maybe sometimes be at low frequencies, sometimes even less than 1 radians per second. Okay, so of the order of 0.1 radians per second and so on, right? In the linear scale, if you look at it, 0 to 1 is a very small region, right? It becomes very difficult for you and me to visualize things. Whereas in the logarithmic scale, we can expand the low frequency region, which becomes very useful for us to visualize what happens in the low frequency regime, right, in practical cases. So that is an advantage of using a logarithmic scale for frequency. Okay. So obviously, of course, if I use the logarithmic scale, I cannot represent 0, right? But then practically, there is nothing called 0 frequency, right? So see, take a sinusoidal input, right? What does it mean to say the sinusoidal wave has 0 frequency? Like that is not practically meaningful at all. Okay, so that is why we have, this characteristic. Okay, now you and I should learn some terms, what is called as 1 decade above and below a frequency. So let us say on the logarithmic scale, if I take some frequency 1, okay, 1 to 10 means 10 is 1 decade above 1. Okay, so if I take a particular frequency, if I multiply it by 10, okay, that range is 1 decade above omega. So in this particular case, I take some frequency omega, I multiply it by 10. So the range omega to 10 omega is called as 1 decade above the frequency omega. Similarly, from 1, if I divide by 10, I go to 0.1. This is a decade below 1. Sorry, excuse me. So this is a decade below 1. So if you take any frequency omega, the range 0.1 omega to omega is called 1 decade below omega. Okay, so I hope this definition becomes clear. Okay, so all of us should know what is a decade of frequency above and below a particular value. Okay. Similarly, there is something called as an octave. So what is this octave? Let us say I have 1 and I go to twice that value, above 1. So if I have any frequency omega, the region omega to 2 times omega is what is called 1 octave above omega. Similarly, if I divide 1 by 2, I get 0.5. This is an octave below 1. Okay, I'm just illustrating as an example. So consequently, the region 0.5 omega to omega is an octave below omega. Okay, so this is something which is important. All right. So, and I hope everyone knows the difference between ln and log. So in your calculator, there are 2 buttons, right? ln and log. What is the difference between ln and log?
ln is natural log, log to the base 10.
Exactly. ln is natural logarithm. Log by default is log to the base 10. Okay. So in this particular course, when you want to calculate measures, please use the log button. Okay. So by default, it's set log to the base 10. Okay. So if you use the ln button, we will start getting natural logarithms. Okay. So I hope the reasons for using a logarithmic scale for frequency are clear. Okay, and what is meant by a decade of frequency and the octave of frequency. All right. Now, let's figure out why we use a decibel measure for magnitude of P of j omega. So once again, please note that magnitude of P of j omega is a positive quantity. See, P of j omega is a complex variable, but when you and I calculate the magnitude of a positive number by taking the square of its imaginary part and the real part, add them and take the square root, we are going to get a positive number, right, as a square root. Okay, so that is why the magnitude of P of j omega will be positive. So when we take the logarithmic or measure of the positive number, we are going to get a positive number. Okay, so that multiplied by 20 will be the decimal measure. Now, same arguments apply. Why? Because once again, using a logarithmic scale, we can demonstrate and display and analyze a large range of magnitudes. Right? Let's say we start from 0.001 to 10 power 4. Okay, you and I can easily plot it in a logarithmic scale. So imagine, right? This is the magnitude of P of j omega in decibel measure, right? You and I can plot a huge range of values using a decibel measure. Okay, so that is an advantage using a logarithmic measure. So once again, just like frequency, you and I can expand the low magnitude region. Okay, so even if magnitude is less than 1, okay, so we can expand that low magnitude region. And very importantly, the feature which we are going to leverage in our learnings going ahead is that we can plot the individual factors of a transfer function and just add them, okay, to get the overall magnitude. Why is this the case? That is because of a very useful property of logarithms. Please remember, log of a times b is log of a plus log of b. Similarly, log of a by b is log of a minus log of b. Okay, so this also can be written as log of a plus log of 1 by b. Okay, so I can write log of a by b as log of a minus log of b, or I can also write it as log of a plus log of 1 by b. Okay, because I can write a by b as a multiplied by 1 by b, right? So both formulae are correct. Now, why is this useful? Now we can come to control, right? Please remember our Planck transfer function. In general, it is written this way, right? Or even our open loop transfer function, for example. So now, when you and I substitute S equals j omega, we get this. Okay, so obviously the magnitude of P of j omega will be the magnitude of the individual factors. Okay, so this is a well-known result from complex theory that if you have a complex function which is a multiple of various factors, the magnitude is going to be the multiple of the individual factors. Okay, so that's what we have. So I hope this transition is clear. Okay, so that is this entire magnitude is going to be the magnitude of the individual factors. Okay, so that's what we have. Now, when we apply the above thing and we want to calculate 20 logarithm to the base 10 P of j omega in decibels, we can start having in the magnitude of the individual factors, because log of a times b is log of a plus log of b. So the first factor is magnitude of k. So we get 20 logarithm to the magnitude of absolute value of k. The second factor is j omega plus z1. So we get 20 log j omega plus z1. The mth factor in the numerator is j omega plus z1. So we get 20 log j omega plus z1. I hope it's clear, right? So as many products we have, they become sums, right? When we apply the logarithm and take the distribution. Now in the denominator, we have 1 by j omega plus p1. We will write it as 1 by j omega plus p1. So this factor will become 20 log of 1 by j omega plus p1. Ultimately, this last factor in the denominator can be written as 20 log 1 by j omega plus p. Okay, so I hope it's clear what advantage you and I get by writing this in decibel measure. All right. So I hope one important advantage of expression in decibel measure is clear. So the idea now is that you and I can plot the Bode plot of the individual factors, and then by just simply adding them, we can get the Bode plot of the essentially the consolidated. Okay, so essentially this is an important advantage, right, of having a logarithmic measure, right, or decibel measure for the magnitude. Okay, so this is why it is called as log magnitude plot. Okay, so once again, I'm reiterating the reason. It's called as a magnitude plot. Sometimes taking the logarithm. Now, what about the phase? So if you have P of j omega, the phase is also very interesting. Okay, so if you have the phase of, let's say, A1 j omega by A2 j omega, that's going to be equal to the phase of A1 j omega plus the phase of 1 by A2 j. Okay, so this is a result from, once again, complex variables. Okay, so we have products of terms, complex terms. The phase of the product is going to be the sum of the phase of the individual terms. Okay, so that's what you and I will have. So consequently, the phase of P of j omega will be the phase of K, which is the first term, then the phase of j omega plus z1, all the way till phase of j omega plus zf. Then we start with the denominator terms, 1 by j omega plus p1, that phase, all the way till the phase of 1 by j omega plus en. Okay? So that's what we have. All right. Okay. So I hope it is clear, how this is, right? So this is something which we will leverage. Okay. So any questions on this part before we move ahead? So in summary, the Bode plot is a visual representation of the sinusoidal plant transfer function or sinusoidal transfer function in general. And it has two plots, magnitude plot, where the magnitude of this transfer function is plotted in decibel measure by taking its logarithm and multiplying by 20. And the phase plot, where the phase is plotted in degrees. Okay. And in both plots, the frequency is plotted on a logarithmic scale on the abscissa. Okay, so this is what we have. Okay, as the Bode plot. Now we can set up things now, right? So now it will be clear why we are learning the Bode plot of multiple blocks. So in general, if let us say the Bode plot, is the ratio of two polynomials in S, which we call as n of S and d of S. Let's say the numerator has m terms, right? n1, n2, all the way till n. Of course, we can also have a k, right? Again k, and then like a denominator has n terms, d1s, dns. So the point is, we plot the Bode plot, or let me say construct. Okay, let's construct. If we learn how to construct Bode plot for each individual factor, and then add. Okay, to get the Bode plot for the given transfer function P of x. So that's what we are going to learn. So an important question comes: what are the building blocks that form the constituents of a transfer function? We can show that given any arbitrary transfer function, by now I'm sure you also will know it, right? The building blocks are going to be these. Okay, so we'll have a gain k, constant real number. We can have an integral term 1 by s. we can have derivative terms. We can have a first order term of the form 1 by ts plus 1. We can also have a first order term of the form ts plus 1. And then we can have a second order term of the form omega n squared plus divided by s squared plus 2 zeta omega n s plus omega n squared. And then we can have the reciprocal, okay, where the second order term can come in the numerator. Okay, it can be shown that you give me any transfer function, we can break it into this. Okay, so let's understand. Okay, let's say I have some transfer function s plus 2 times s plus 4 times s plus 1. Okay, so just I'm taking arbitrarily. So this I can write as 2 times 0.5 s plus 1. Then the denominator, the first term I can write as this. Second term I can keep it as s plus 1. Then this becomes 0.5. 2 by 4 is 0.5, right? I'm just simplifying. So 0.5 times 0.5 s plus 1 divided by 0.25 s plus 1. Okay, so immediately you can see that there are 4 terms, 0.5, 0.5 s plus 1, 1 by 0.25 s plus 1, and then 1 by s plus 1. So these are the 4 terms, building blocks, which come in this platform. So you can see that I just took a simple example, right, to show that this can be done. On the other hand, let's say there is a s term here. So what will happen is that we'll have a s term here, and then we'll have a 1 by s coming in. Okay, right? So you can see how we are able to break down any transfer function, right, as a product of these building blocks. Okay, so that is an important observation for us, right? Okay. So the bottom line is that if you and I are able to plot the Bode plot of these individual constituents, and then we essentially go ahead and plot them, right? And then add all the Bode plots, we have the result. Okay, so I hope it's clear why we are dealing with the specific building blocks. Now, at this point, one may wonder, hey, look, I'm in the automotive industry, right? I am dealing with control of automotive systems. Like, why should I learn all these things? It so turns out that even in automotive applications, if we look at frequency response to study the system characteristics, let's say we have a brake system or a steering system and so on, right? And then you and I do experiments, right? Or a traction motor and so on, right? So we do experiments to figure out the relationship between inputs and outputs. We do a science week test, and we look at the Bode plot, right? It so happens that by and large, the lower order model that people will construct for a plant transfer function, even in automotive applications, will by and large contain these terms. Okay, the integral term, the derivative term, the first order terms, and the second order terms. Okay, so if you and I are able to know what is the Bode plot looking like for these terms, we can then reverse engineer the transfer function when we get the Bode plot in experiments, right? So if you recall, that is one of the important agenda of this course, right? We have to look at experimental data and figure out, hey, okay, this controller may work, right? This transfer function may fit the system and so on, right? That is an important aspect that we have. All right. Okay. So this is what we have. So that is why you and I are going to study these blocks. Okay, they are quite useful in practice. Okay, so let's start looking at each factor one by one. First, let's start with the factor which is the gain k, right, or the scalar k. The k is a real parameter. So there is no s here. So d of j omega just is k. Okay. So the magnitude of j omega is magnitude of k in absolute measure of 20 logarithm to the base k in decibel measure. The phase of g omega, this k is going to be 0 degrees if k is greater than 0, or plus or minus 180 degrees if k is less than 0. So that's how we plot the thing. So in this example, we have taken k to be 10. So if I want to calculate the magnitude of 10 in decibels, I take the logarithm to the base 10 and multiply by 20. What is the logarithm to the base 10 of 10?
1, sir.
1, right? So we get 20 decibels, right? So I hope it's clear how we got this curve. So, but this is independent of omega, right? So that is why you and I have a straight line, okay, in the what is it, magnitude plot. And on the real axis, so this in the complex plane, 10 lies on the positive real axis. So the angle is 0. Okay, so that is why when we plot the phase curve, we plot an angle of 0, right? So I hope it is clear how we got the Bode plot of this constant, right? A very simple and straightforward example for us to get started. All right. So once again, please stop me whenever there are questions. Okay. So what I will do that I will keep continuing because tomorrow's class portion also I will get started because tomorrow's class also is going to be very involved. So let's continue to the best extent possible and then we'll go from there. Right. Okay. So the second factor is 1 by s. Okay, which is the integral term. Right. So now things become interesting. Okay. So please note that the first factor, which was the simplest term, it was just a constant parameter k, right? So there was no s term. So here there's an s term. So when you substitute s equals j omega, so what happens is that like we have 1 by j omega. Okay, so that we can write as, if you multiply the denominator and numerator by j, you get j divided by j squared omega, which becomes minus j omega, right? That's what happens. So if we take d of j omega to be 1 by j omega, and if I have to evaluate the magnitude of 1 by j omega, what did we learn just now in complex variable theory? The magnitude of the ratio of two complex variables is going to be the ratio of the two individual magnitudes. So what can you say about the magnitude of 1 by j
It will be 1 by omega.
It will be magnitude of 1 divided by magnitude of j omega. Okay, correct? Yeah, yes, Roshan. We will ultimately get to that answer. I'm just showing the intermediate steps once.
Yes, sir.
Right?
Yes, sir. Thank you, sir.
Yeah. So this will be the magnitude of the numerator to the magnitude of denominator. Magnitude of 1 is 1. Magnitude of j omega is 1 by omega. So that's how, magnitude of j omega is just omega, right? How did we get this? Because magnitude of any complex variable is the real part square. Real part in this case is 0. The imaginary part square is omega square. You take the square root, we get it. All right. So this is what we have. All right. Okay. So, but then we need to take the decibel measure. So if we take 20 log to the base 10 1 by omega decibel, what happens to logarithm of 1 by omega? It is minus log omega, right? I hope it is clear how we got this, right? So log of 1 by omega is going to be minus log of omega, right? So how did we get this? A minus log of b, right? So this will be log of 1 minus log of omega. What is log of 1? 0, right? So we get 0 minus log of omega. So we get minus. Okay, so this is the magnitude in decibel measure. Now the phase of 1 by j omega is going to be minus 90. How did I get this? Because it is going to be the phase of 1 minus the phase of j omega, right? Phase of 1 is 0 degrees and j omega is the positive real axis, right? That angle is 90 degrees. So we get 0 minus 90. That becomes minus. I hope it's clear, right? How we get this. All right. Fine. Any questions on how we got the magnitude and phase of 1 by j omega 1 by s?
Sir, the reason why we are using 20 log scale is because of that power relationship with respect to signal.
Yeah, exactly. So what happens is why are we using the decibel measure, right? It so happens that when we it has to do with the power spectral density, right? So if you are essentially doubling the power, right, this decibel measure will get increased by 20. Okay, so essentially we are essentially going to use that idea as we go later on. Okay.
Understood, sir. P is basically proportional to V square for those reasons.
Exactly. Right. I'm sorry. I think someone else is asking the question. I'm sorry. Can you please say your name? No.
Prem
Oh,
here,
it's
sir.
Prem. Okay. Your voice sounds different.
Yeah.
Right? But,
No, sir. I was a little bit distant from the mic, maybe.
okay. Fine. All right. Okay. Fine. Yes, Prem. So essentially, you and I are going to use those ideas. So I'm only using as I keep repeating, I'm only using results. Okay. So I'm not going into the back into the theory, but whenever I think, please keep the questions coming. Whenever such fundamental questions come, I will share information to the best of my knowledge. Okay. So the reason why we use this decibel measure is motivated by the spectrum analysis frame. So in fact, this will become useful when like we do what is called as bandwidth analysis, right? So when the power of a signal is halved, okay, the decibel measure, sorry, I told 20, right? Sorry, decreases by 3 decibels. It should not be 20. It's 3 decibels. Okay, when the power of a signal is halved, the decibel measure decreases by 3 decibels. Okay, so you will see such definitions coming in. Some people will start looking at a frequency at which the signal magnitude will become 3 decibels lower than the zero frequency value and so on, right? The reason is the same. The reason is this. Okay, so that physically, whenever you have the power of a signal getting halved, okay, the decibel measure will decrease by 3 units or 3 decibels. Okay, so that is one more interpretation we have. All right. Okay. So where are we? All right. So now we know that you and I.
Sir, just one question.
Yes, please. Please go. Yes, sir.
Yeah, what's the, I mean, we understand the reason for using frequency versus amplitude, but what will be the benefit of using frequency versus phase?
Frequency versus phase also. You will be able to figure out whether it's a minimum phase system or a non-minimum phase system. Okay, we'll come there. All right. See, when you essentially want to, may know who asked the question? I'm sorry. Keshav, what happens is that if you use a log magnitude plot alone, you get a lot of information, no doubt about it, right? But then when you want to figure out the transfer function, there is an interesting result which you and I will look at later. Okay, where if you look at what happens to the phase of the system as omega tends to infinity, you and I can get n minus m. See here, you remember we had m factors in the numerator and n factors in the denominator, right? So there is a relationship between n minus m and what happens to the phase. All right. So when we conduct experiments, you and I can figure out n minus m from that data. Okay. So that is one reason why we also need the phase.
Fine, sir. Okay.
See, sometimes if you assume some structure of the plant transfer function and you assume that is reasonable, yeah, you will end up using the magnitude plot by and large, to get the coefficients. That I will call it as a semi-inverse approach. See, what is the forward approach? Forward, okay. What is the inverse approach? You have the Bode plot, you get the P of S. But then, what is an intermediate? You assume a structure of P of S that is based on your experience, right? Without P of S being a black box, you assume a structure for P of S and then use the Bode plot to fit the parameters in the structure. Okay, then by and large, you may end up using only the magnitude plot. I hope that in a broad sense answers your question.
Yeah, I thought maybe we are using it to identify whether the signal is a noise or the internet signal.
So so you will anyway have noise. Okay, so see when you do the project, you will see. Okay, so see although the Bode plots are nice straight lines and curves here in my notes, right? When we present the actual data, you will see that it's all over the place. Okay, so that's why we need to use our imagination and then also our understanding of all these what to say concepts to sort of like solve the inverse problem. Okay, so that is why this method I call it as a semi-inverse method, right? So where you, based on experience and domain knowledge, you assume a structure and then like fit the parameter. Yeah.
Okay, fine.
Interesting arguments here, Keshav. Okay, in addition to theory. All right. Fine. Okay, so now let's go back to the Bode plot. Okay, so let's come to the phase plot first. The phase plot is going to be pretty easy, right? Because irrespective of the frequency, it is always at minus 90. So it's a horizontal line in the phase. Now let's draw the magnitude plot. So the magnitude is minus 20 log omega decibels. Now, how do I do this? For this, we can typically construct a table. Okay, so when let's say we plug in some values of omega without loss of general. When we plot omega equals 1, what do you think will happen to the magnitude? It will be log of 1. What is log of 1?
0, 0.
0, right? So the magnitude will become 0 degrees. Now, by and large, see, once again, this is a convention, right? So we tend to plot the Bode plot in a frequency range of interest. And also many times we plot, I think someone has a question. Yes, Roshan, do you have a question?
No, sir. I'm sorry.
So typically we plot it in a range of interest, and also we may plot in a decade above and below the frequency range of interest, right? So here we started with 0.1, sorry, omega equals 1. Let's also figure out what happens at 0.1 and 10. Okay, so if we know 0.1 is it 1 decade above 1 or 1 decade below 1?
Below 1, sir.
Below 1, right? So when you substitute 0.1, what happens here? What is log of 0.1?
It will be 20, sir. Basically, 0 minus 1 upon 10, we can write.
Log of 0.1 is minus 1, right? Is it? I hope I'm right? So
Yes,
log
sir.
of 0.1 is minus 1. So minus 20 times minus 1 will become plus 20, right? That's why the magnitude came out to be plus 20 decibels. I hope that's clear, right? Okay. So now let's say we go 1 decade above omega, right? Sorry, above 1, which is 10. If you and I want to evaluate the magnitude, it becomes minus 20 log 10. We know that log 10 is 1. So the magnitude comes to be minus 20. Okay, so that's how we get this, right? I hope it's clear how we got these values, right? So the blue curve here is the magnitude plot of 1 by S. So what do? We essentially put 0 decibel, 20 and minus 20. Those are all equidistant, okay, on the y-axis. At 1, we have 0 decibels. At 0.1, we have 20. And then at 10, we have minus 20. So you can see that it's a nice straight line that passes, okay, in the decibel metric. Okay, so that's what happens. And what is the slope of this line? The slope of this line is minus 20 decibels per decade. Why do you think it's minus 20 decibels per decade? So let's
Sir, it
say,
is
Minus
Sir,
20 to
negative
minus
slope.
20,
ah,
20
so-
to minus 20 between 10 to 0.1.
So let's reason it out, right? So when you go from 0.1 to 1, which is 1 decade, what is the change in the magnitude? Goes from
It is
20,
multiplied by 10.
no, yeah, multiply by 10, correct. What is the change in the magnitude? It goes from 20 decibels to 0 decibels. So what is the change?
It is negative, sir. Basically, negative slope.
It is decreasing by 20, right? Am I correct? That is why it's minus 12. Similarly, if we go from 1 to 10, this is another decay. What is the change in magnitude? The slope of the log magnitude curve of 1 by s is minus 20 decibels. Is it clear? Okay, so let's plot the same thing. Sorry, at omega equals 1, it is 0. I want you to tell me what is the value of the magnitude 1 octave above 1, below 1. So when omega equals 0.5, can you substitute and tell me what will be the decibel measure? Is anybody?
I'm doing, sir. Just a minute, sir. Doing, sir.
So you just
Sir, it's
substitute
minus 6.
Minus 6.202.
Minus 6.
minus 6, but then there is a minus sign outside.
Right.
So
Yes, sir.
Plus 6.02. Right.
it is, yeah, let me just round it off to 6,
Yeah.
right? So just for the sake of demonstration. So does everyone agree that at 0.5 it is 6 decibels? Right? Similarly, what will happen when omega equals 2? Can you find out, please?
Uh,
It's
6.02.
minus
But
6.
then there's a minus sign outside in the magnitude expression, right? So it becomes minus 6. So you can see that when we go 1 decade above 1, we are decreasing by 6 decibels. Similarly, from 0.5, if we go 1 decade above, once again, we are decreasing by 6 decibels, right? So what is the same slope in decibels per octave? So
Minus 6.
minus 6, right? Very good. Okay. So in terms of decibel per decade, we go minus 20, right? Minus 20 decibels. So when we go from 1 octave, from a frequency to 1 octave above it, we decrease by 6 decibels. Okay. So that's why the slope becomes minus 6 decibels. Is it clear how we got the Bode plot of 1 by s?
And it can be calculated like, sir, basically, if I'm not wrong, sir. Hello.
Yes, please.
Sir, basically, this slope can be calculated as 6 minus 0 divided by 2 minus 1, right, no, sir? Like y2 minus y1 divided by x2 minus x1.
Okay. You need to be a bit careful here, Roshan, because it is not x2 by logarithmic scale.
Oh, okay.
So kindly be careful. I have not plotted it on a linear scale. Okay, so that is why I'm using this logic.
Sir, yeah, inline to this only. Means when we are writing this is 20 dB per decade. It is not going to be linear, like, right? Means if we consider this example, 0.1 to 1 is 1 decade. Okay, so 1 decade above 0.1 is 1, but if we say 1 to 1 and 1 to 2,
1 to 10, 1 to 10.
so 2 decades above 0.1 is 1 to 10.
In that region, it decreases by minus 40, right? So you divide by 2, you get minus 20 decibels, right? Is it not because? See, this is a convention, Vikas. Okay, so please don't interpret it as y2 minus y1 by x2 minus x1. Then we will get a little bit off track. Okay, so Vikas, to complete your question the way I understood it, you go from 0.1 to 1, that's 1 decade above 0.1. We decrease by minus 20, right? Or we change by minus 20. If I go from 0.1 to 10, we are going 2 decades above. We change by minus 40. So minus 40 by 2 decades will be minus 20 per decade. Is it correct, Vikas? We get the same.
Yes, sir.
Right? So please note, this magnitude plot is only a straight line in this special, coordinate or axis system that you and I have chosen. Okay, so it is not, if we didn't choose a decibel measure and if we didn't choose a logarithmic scale for omega, it's going to be a nonlinear curve, right? Please kindly note that point. Okay, right? Is it clear?
Right, sir. Clear, sir. Clear.
Yes, sir. Yes.
Okay. So I think this is a good place for us to stop. We just went into the integral factor. So tomorrow, what we will do continue, so that in real life, if we encounter some transfer functions, we should be able to break it down into these individual constituents. Okay, so that is the motivation of fine. Okay, Arunachandam, is everyone present today? Thanks.
Yes, sir. Everyone is present, sir.
Okay. And as we agreed, I think your midterm will be on March 9th, right? So March. Right?
Yes,
So,
9th March.
I hope everyone will be able to come to the department in person. And then, yeah, all right.
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. We are coming, sir.
Okay. All right. So we will anyway keep continuing with our theory class so that we can get all the theory concepts. Then I will request Abhinav to start the projects, because he will also come to these sessions and then share the problem statements for the projects with you, and also have some help sessions so that you are able to solve the projects and submit, okay, by the end of the semester. Right? Okay. So we will have those sessions as we go. All right. Okay. Any other questions before we close?
Sir, in continuation.
Ah.
Sir, yesterday, last class, there was a discussion about significance of amplitude. In last class, when we were discussing about amplitude, we derived that amplitude might not have a significant play. I would like to just, can you go back to?
Amplitude may not have a significant play. I don't understand. Maybe I'm missing.
Yeah, sorry.
Should I keep on scrolling up?
Just 1 minute, sir. Yeah. Sir, maybe tomorrow I'll just go to that slide.
No problem. You can go through the notes and then which one? Okay, so where should I stop?
Sir, tomorrow I'll here, but tomorrow I'll come back, sir.
Okay. No problem.
Yeah.
Sure. No problem. Okay, then we will continue tomorrow at 5. Okay, and then we will go from here. All right. Thank you.
Okay.
Thank you, sir.
Thank you, sir.